Hi everyone. So in this video, we're going to be getting a little bit more practice with applying these shifting transformations that we talked about in the last video. So what we'll see in this video is that you can do more than one shift at the same time to a function. So we'll be looking at examples that do that all throughout this video. And then another focus of this video is that rather than dealing with functions like f of x is equal to x squared or f of x is equal to square root of x and just transforming those, we're going to do an example where the sort of parent function, the beginning function that we're using, is a function where we're not given any kind of equation for it. And so that's going to be an example where you really do have to know how transformations work in order to graph the transformation, because you're not going to be able to just rely on plugging in numbers. So we'll get to that. That'll be our last example in this video. So just to quickly remind you, what we saw in the last video is that basically if you add or subtract numbers to your function or to the input of the function, that's always going to be a shift. So in later videos, we'll see that there's other things you can do to stretch your graph or to flip it in different directions. But if what you're trying to do is just take a graph and pick it up and move it, you're always going to accomplish that by adding or subtracting. Specifically, if you add or subtract a number to the function as a whole, that is going to be a vertical shift. So if you add a number to a function, that's going to shift your graph up by that many units. And if you subtract a number from your function, that's going to shift the graph down by that many units. So basically with vertical shifts, they go in the direction that you would expect. Addition goes up, subtraction goes down. And then what does that actually look like in the graph? Well, in order to accomplish that shift, you're going to either add or subtract whatever your shift is from every y coordinate, because y coordinates correspond to the vertical position. Now, if instead of adding or subtracting your number to the function as a whole, if you're adding or subtracting a number to your input, so to x, that's now going to be a horizontal shift, right? Because you're changing the inputs, and inputs correspond to x coordinates on the graph, which are the horizontal position. And so the one thing you have to remember about horizontal shifts is that they go kind of the opposite direction than you would expect. So if you're adding a number, that's going to actually shift your graph to the left. Whereas if you're subtracting a number, that's going to shift your graph to the right. And we talked about why that is in the last video. So I'd recommend, if you still want to understand why that is, to go back and look at the last video. I'm not going to linger on that in this video. So how do you actually accomplish these horizontal shifts? Well, just like with the vertical shifts, you add or subtract your number, and you either add or you subtract it from the x coordinates this time, because we're talking now about a horizontal change. Okay, so let's look at an example. So this first example we're going to use transformations to graph the function g of x is equal to x plus 3 squared minus 1. So when I say use transformations, we did some examples like this in the last video. Basically, that means that we're not going to make a table. We're not going to say, okay, g of 1 is equal to blah, blah, blah. G of 2 is equal to, of course you could do that. But the whole point of this unit is to show you that that's not the only way. And as I mentioned, there are situations where using transformations is a lot easier than plugging in numbers, or in some cases, it's kind of the only way to do a problem. Okay, so the first step when we're using transformations is to figure out, what is the kind of basic function, basic shape that this is a transformation of. So the basic graph that we should be comparing this to, well, this is x plus 3 squared minus 1. And so what is the function that we're kind of doing some changes to? Well, f of x is equal to x squared, right? Because basically we can see that here, what are we doing? We're subtracting 1 from x squared, and then we're also adding 3 to x. And if we do those two changes, that will give us this function. So our basic graph, our parent function is x squared. So I'm just going to go ahead and sketch the graph of x squared, and I'll actually kind of highlight a few key points that are on the graph. So we talked about this a little bit last time. If you just have like just a handful of points that you know lie on the graph, that's going to really help you to do these transformations. Okay, so that is our original graph. And so now the question becomes, how can we see g of x? How can we see that as a transformation of f of x? So basically we're looking at, what are the things that we're adding or subtracting, and what are we adding or subtracting them from? So for example, here we see that we're adding 3 to x. And so we know that if you're adding or subtracting from x, that's a horizontal shift. And we know that they go the opposite direction as they seem like they should, right? So a horizontal shift, if you're adding, is going to be shifting to the left. Whereas this subtraction of 1, well, we're not subtracting 1 from x, right? So we're subtracting 1 from kind of like the whole function, right? It's like you're doing x plus 3 squared and then you're subtracting 1. You're subtracting 1 at the end. And so that means that it's going to be a vertical shift, and vertical shifts go kind of the way you would expect. So shifting or subtracting 1 is going to shift down by 1 unit. So by the way, I'm going to just show you kind of one other way of writing this down, and this is what we did in the last video. If you wanted to, you could also rewrite g of x as f of x plus 3 minus 1. Right? Because what we know that f of x is x squared. What is f of x plus 3 then? Well, that would be x plus 3 squared, right? So forget about the minus 1 for a second, focusing now on the fact that our original function was f of x is equal to x squared. If you were trying to evaluate f of x plus 3, that would be x plus 3 quantity squared, right? And then this minus 1 can just come at the end. And so if you wanted to, if you want to be able to kind of rewrite your function so that it looks more like the stuff on this table, you can always do that, right? So you can rewrite this function g of x in terms of f of x. However, I don't really think that's necessary. I think maybe the easier way to do it is just to recognize that whenever you're adding or subtracting from x in your function, without having it written like this, but just kind of within the function itself, whenever you're adding or subtracting to x, that's horizontal. Whenever you're adding or subtracting kind of to the whole function, that's vertical. Okay, so all that being said, now we're ready to sketch the graph of g of x. So how do we do that? Well, we can focus on our key few points here. And what we're going to do is we're going to shift each of those points to the left 3 and down 1. So I'm going to go left 3, down 1. So that's our first point. Left 3, down 1. Left 3, down 1. Left 3, down 1. And left 3, down 1. And the nice thing about parabolas is they're also symmetrical. So you could even just do kind of half of it and then just replicate the other half using symmetry. And so that means that we're going to get a graph that is shaped like this. So that is our graph g of x. Okay, so let's do another example kind of in the same vein. I don't know what is going on with that. Let me delete that. That is gigantic. Okay, so this next example, again, we're going to use transformations. To graph, let's call it h of x is equal to absolute value of x minus 1 plus 2. So again, the first thing we probably want to do is identify, what is the basic function that this one is a transformation of. And so the basic graph that we want to compare this to, so in the last example, what was like the main action of the function? It was squaring, right? And so that's how we knew that our function was x squared. Whereas this one, what's the main kind of action that's going on in this function? Well, we're taking an absolute value. And so that tells us that our basic function we can compare it to is f of x is equal to absolute value of x. So we can start by sketching that function. I'm going to plot just a few points here. The nice thing about absolute value functions, though, is that really all you have to know is that they have a slope of -1 on the left and 1 on the right, right? So we're kind of just perfectly going straight through diagonally at like a 45-degree angle on both sides. Okay, so that is our original graph. And so what is the transformation? Well, let's write down the function. So the function was h of x is equal to absolute value of x minus 1 plus 2. So again, we start by looking for, what are we changing in this function, and what, how can we interpret that change in the graph? So we can see that we're subtracting 1 from x, and so that tells us it's going to be a horizontal shift. Specifically, we know that horizontal shifts go kind of backwards of what you would expect. So if we're subtracting 1, that means we're going to shift to the right 1 unit. And then here we're adding 2. We're not adding 2 to x, we're adding 2 to the whole function. And so that tells us that it is a vertical shift, and specifically it's a shift that is going to go up by 2 units. And just to show you again, like I did on that last one, if you wanted to, you could also rewrite h of x as f of x minus 1 plus 2. And then you could really see how that matches up with the stuff that we have on that table. But the important thing is, again, just whether you're making changes to x or to the function as a whole. Sort of, you can think of it as like the inside versus the outside of the function, right? The inside of the function is inside the absolute value, outside the function is outside the absolute value. And the last one, inside the function was inside the squaring, outside the function was outside the squaring. Okay, so now we just want to apply this transformation. So I'm just going to take each of these points that I did here, and I'm going to shift them to the right, and then right 1 and up 2. So right 1 up 2, right 1 up 2, right 1 up 2, right 1 up 2, right 1 up 2. But with this one, I think even if you just take that kind of middle point, I'll show you what I mean by that in a second once I'm done sketching this. But if you just, instead of even taking all of those 5 points we just did, if you just focused in on this point here and just move that to the right 1 and up 2, then you actually would you could sketch the graph from there, right? If you're familiar with the shape of the absolute value graph, you don't have to bother with plotting all the points. You can just kind of extend the shape of the graph. And really the same argument could be true for a parabola as well. So if you're familiar with like the kind of shape of how the parabola goes up, you could focus in on this point. This is called the vertex. You could focus in on where did this point go. So this point went to the left 3 down 1, and then from there just kind of extend your parabola. But if you're ever uncertain, you can always, just like focus on a few points and kind of track those points. Okay, so we're going to do an example now where we're going to be kind of working backwards. So we want to find an equation, or find the equation of the function that we have graphed right here. So this is just basically working backwards. So instead of being given an equation and using transformations to graph it, this time we're taking a graph and we have to interpret it in terms of transformations. So in a lot of ways, this is really similar to the other problems, because we first need to figure out, what is the basic graph? Like, what shape are we looking at here? So we have to be able to recognize which kind of a shape this is. So the basic shape we're looking at in this case is a square root graph, right? It's a square root of x. And so if we had just the regular square root graph, that would look like this. So we just need to figure out, how has this been transformed? What are the transformations that are happening from the purple graph to the green graph? So, we're just talking about shifting. So we really just have to keep track of where did this, look at like one point and see where that point moved. So originally the graph would have a point at 0, 0. We can see that our graph here has a point instead at -1, -3. And so what we can say is that this graph has shifted to the left by 1 unit. And then we can also say that it has shifted down by 3 units. And so now we just need to figure out what that would look like in our formula. So we can start by, if you want, applying them actually just straight to f of x, right? So we can rewrite this as f of x minus 1, or sorry, x plus 1, because we're shifting to the left, minus 3. Right? That's how, just using the kind of function notation, that's how we would say shift to the left by 1, shift down by 3. So what is that actually going to come out looking like in our equation? Well, if we were just doing f of x, that would be square root of x. So what is f of x plus 1? That's the square root of x plus 1. And then this minus 3, well, that's outside of the function, so that just gets tacked on at the end. And so putting this all together, we can, maybe let's call this function k of x. So we can call this function k of x is equal to the square root of x plus 1 minus 3. So once again, you could, if you wanted to, like skip this step. If this step feels confusing to you, you're welcome to skip it. You don't need to write out all this, stuff in function notation. The important thing, again, is notice that when you're shifting to the left by 1 unit, that shows up inside the function. So in this case, shifting to the left by 1 means you're adding 1 to x, and that means that you're adding 1 inside the square root. Whereas shifting down, well, that ends up outside of the square root because it's a vertical shift, and that is kind of the outside part of the function. So regardless of whether you choose to ever write it like this, you should just basically be able to recognize how does the inside versus the outside of a function look for different types of functions. Okay, so we're going to do one more example. So in this example, as I mentioned earlier, this is a function where we're not given a formula. And you could come up with the formula of this. It would be a piecewise function, but it would be a piecewise function with like 4 pieces. It would basically be a really big headache to try to do the transformation using like the equations or plugging in points or anything like that. We really want to apply this transformation just in terms of looking at the graph. So let's say that this function is called f of x. So what we're going to do is we're going to use transformations to graph. So the function we're going to graph is going to be f of x plus 2 plus 3. Okay, so let's look at this, this formula, or this kind of transformed function notation, and figure out what's going on with it. So what does it mean, or what does it do when we add 2 to x? Well, we know it's a horizontal shift, and specifically, this is going to be a shift to the left because we're adding. And so we're going to shift to the left by 2 units. And then what does this plus 3 do? Well, we're going to, sorry, I don't know why I said add. We're going to shift it now vertically, right? And so in this case, vertical shifts are going to go the way that you would expect. So we're going to shift up by 3 units. So we're never going to write an equation for this. We're never going to plug in any points or anything like that. All we're going to do is take this picture that we have and do this. We're going to shift it to the left by 2 units and then shift it up 3 units. I'm just going to change the color of this. So we do probably want to pick kind of a few key points on this graph that will be kind of tracking as we do this transformation. So we already have these 2 endpoints. I'm just going to put a few other points on the graph that we can kind of keep track of. And then the only other thing we have to do is really make sure that we're being consistent with the correct shape between them. So, if you wanted to, you could add like these 2 points. I'm going to keep them off because I think as long as we remember how this graph is shaped, we can do it with fewer points. So we're going to take each of these points and we're going to shift it to the left 2 and then up 3. So I'm going to start with this one, left 2, up 3, left 2, up 3. So we can already see that is our first little snippet of our graph. Now we're going to take this kind of bottom point from the sort of parabola looking part, left 2, up 3. That's going to put that point here. Then we have this point up at the kind of right end of the parabola looking shape. We're going to go left 2, up 3. And so now how does this kind of middle part of the graph look like? Well, if we just remember the fact that it came from the curved portion below, we can just kind of mimic the shape of that curved part, right? Because the important thing to know about shifts is that they're not going to change the shape of the graph. They're just going to pick it up and move it. So everything should have the same shape when you're done. Okay, now we have this point that is here. We're going to go left 2, up 3. That's going to put this point here. And then we have our last point, left 2, up 3, and that's going to put that point here. Oops. And so that is our graph. And so again, it's always a good check, I think, especially on this type of a problem. Just like look at your graph and make sure the shape of it looks the same as the one you started with. I think it's really easy to make a little mistake in how you're doing things, and once you kind of connect all the dots, if the shape of your graph looks like smushed, or one of the slopes changed or something like that, that tells you something is wrong. And so yeah, the shape should look the same as the original shape. All right, so that is it for this video. I really recommend looking at the worksheet to practice this stuff. And in the worksheet, I also ask you to find the domain and range of the functions that you're transforming, just to kind of do a quick review on that and hopefully give you a little bit of insight into how transformations affect the domain and range. So make sure you check that out and do the domain and range part of the worksheet as well. All right, I'll see you all in the next video.